Start sharing. Okay, so we are going to now see the details of our plane sweep algorithm, and I'm going to show you an interactive website that is actually showing the steps of the algorithm very well. All right, so we have the planes. Our plane sweep is going to in the book it's shown as a sweep line that is going downwards. On the slides, it's a sweep line that is going from left to right. So I'm going to directly jump to this. On the slides, there is an alternative algorithm, which is divide and conquer algorithm, which is also O n log n. But I'm just going to show you the Fortune's algorithm, which was proposed by Steve Fortune in 1987. It's a sweep line algorithm for Voronoi diagrams. It appeared in the journal Algorithmica. And this animation on the slide that is actually that applet is really out. I mean, no longer exists. Applets are no longer used. Thanks to WebGL, we have better visualizations now. So we talked about the parabolic front. And this parabolic front, actually, this will be the stutter structure of the sweep line. It's not stored explicitly as parabolic equations. Actually, the only thing that we need, I'm going to now show you on the whiteboard what we actually store on the stutter structure. The stutter structure will still be a balanced binary search tree, but it will be something like this. If we have a number of sites, some of them are above here. Let me try to make them a little larger. So what we actually store on the stutter structure will be clear in a couple of minutes. Okay, so let's number them. 1, 2, 3, 4. And this numbering is arbitrary. I'm just numbering them arbitrarily. It seems like they're from left to right. Yeah, it may be from left to right, actually. Yeah. But doesn't. We're actually sweeping downwards. Okay, so this numbering could be something arbitrary. And imagine we have a parabola here, another parabola due to this number, to number 3, maybe another parabola 6, 8, 9. Maybe it's like this. So the sites that contribute to the beach line are 1, 2, 5, 6, 8, and 9. All right. So what we actually store in the stutter structure are these site IDs only. And the way we do that is something like this. For example, they appear at the leaf nodes. Each parabola, let's call them parabola, but we actually just store the site information. One here. And let's have 2 here. And how many I have here? 6. So 1, 2, 5 maybe in one branch. 6, 8, 9 maybe in the other branch of the stutter structure, which is a balanced binary search tree. So we can do something like this. Now the important thing, the reason I'm drawing this tree is to show you what we store at the intermediate nodes. And we have the root node. So this is our tree. At the leaf nodes, we have these parabolas from left to right, as you can see. 1, 2, 5, 6, 8, 9 are our parabolas, and we don't actually store the parabolas explicitly. We just store the site. Site 1, if you know the location, if you know the site 1 xy coordinates, if you know this sx and sy, okay, for a given sweep line position, the parabola is just defined by an equation. That equation can be formed on the fly as you move the sweep line. So it's dynamic. These parabolas are going to get larger and smaller and they are dynamic. So what we store is not the actual fixed parabola equation. We just store the SXSY site information at the leaf nodes. And here, the intermediate nodes, semantically, they indicate the breakpoints. They say that 1 and 2 are neighbor. They are two neighboring parabolas. So we store pairs of sites at intermediate nodes. Now here at this intermediate node, we store not 1 and 5, it's actually 2 and 5, because this intermediate node is going to indicate the breakpoint between 2 and 5. So you can consider this for an intermediate node. What we store is the breakpoint between the rightmost leaf node on the left subtree and the leftmost leaf node on the left subtree. So here at the root node, we store the pair 5 and 6. Okay, this pair 5 and 6 is stored, which indicate this breakpoint between these two parabola parts. And here we are going to have 2 and 5. And that's another pair. We have here 6 and 8. So when we are having just two leaf nodes, it's really easy. Just plug it, put a pair like this. And for another intermediate node, as I said, it's the rightmost leaf node. It's going to be 8 and 9. So this is the study structure. The study structure is nothing but a balanced binary search tree, which contains the sites at the leaf nodes. And actually, each of these sites, they're not all of the sites we have processed up to now. These are the sites that contribute to the beach line, okay, the wavefront. And they have parabolas from left to right that appear on this. And the intermediate nodes are the breakpoints. They are the places where two parabolas meet. And it's not a surprise that these breakpoints, since they are equidistant to these two sites, 8 and 6 for example, they will be tracing out the edges of our Voronoi diagram. So these breakpoints between parabolas, they trace out here, as you can see, they trace out the edges of our Voronoi diagram. Now, let's look at a vertex of the Voronoi diagram. Now, I'm going to show you that show you this vertex information on this interactive website. But as you can see, I've not described how the study structure looks like. And when a new site appears, let me also talk about how we handle a site event. When a new site appears, on the sweep line, when we are handling a site event, what happens is that at that point, a parabola appears. And the first time the parabola appears, the first time it appears, it's a degenerate line like this. It's the degenerate parabola. There's a single line. The first time it appears, it's going to be a line like this. And as we move the sweep line down, it's going to get larger and larger like this. But it's going to we can find, for example, when we encounter a site event with a certain xy coordinate, we can actually search on our study structure to figure out which parabola it hits. So we can find this 2 here by searching in log n time. For example, this 5 and 6. This is the 5 and 6 breakpoint. We can use the parabolic equations of these two to find the equation of the breakpoint to edge and ask the question saying that the x coordinate, if I give you an x coordinate of my event point that I'm handling, is it on the left? Is it to the left of this breakpoint, or is it to the right of this breakpoint? Although the mathematical equations may be quite complex, it's still all one time. So the key and queries that we make at the intermediate nodes are still, is it to the left or is it to the right queries? And at this point, since we do not have fixed equations, we form the equations for a particular So we have 5 and 6. We know the sites 5 and 6. At this event point, we use this y coordinate. The y coordinate of the event point is used to form the parabola equations, because at that specific y coordinate, we will have some specific parabolas. And they may shrink, or they may enlarge, but they will only disappear or appear at certain event points. When you're continuously moving downwards the sweep line, the order of these parabolas, their shape is going to change, but the order of the parabolas will not change. They will remain the same. So, but they may get smaller. So this breakpoint may be moving to the left or right. So depending on where we are currently, depending on the current y coordinate, we will ask this question: is this x coordinate to the left of this breakpoint or to the right of this breakpoint? If it's to the left, as in this case, for this event point, we move to the next intermediate breakpoint. Now we look at the breakpoint between 2 and 5, which is this one. Now we are going to ask the same question: is this x coordinate to the left of this breakpoint or to the right of this breakpoint? And it's to the left. And then we come to 1, 2. This is the breakpoint. Is it to the left or the right? We come to a leaf node. It's to the right. And we end up at a leaf node, which is the parabola of site 2, which means that this new site event is going to appear in the middle of some parabola, and it's going to divide it into 2 parts, which tells us that some of these sites may appear multiple times as leaf nodes. Okay, for example, after the introduction of this new breakpoint, let's call it number 11, site 11. If this site 11 appears, what will happen is that we will have a certain part that belongs to site 2, another part that belongs to 11, and another part that also belongs to site 2. So it may appear more than once on the beach line, but it's not going to be quadratic. Okay, the number of times a site will appear is going to be, again, linear. But it may appear multiple times. A leaf node may appear. So these 2 parabolas may be part of the same site when 11 appears in the middle. So let me just show you how it will look like on this website. I'm going to paste the link of this website on the chat box. Okay, and there's also another interactive Voronoi diagram. I'm also pasting this in the chat box, which is done with WebGL. This one is not about the fortunes algorithm. It's just like an interactive Voronoi web site, which you can add points by clicking, and as you click, the Voronoi diagram is created on the fly, so you can just experiment with it to see how different configurations will use what kind of Voronoi diagrams. And also you can click to a point and you can move it and see how the Voronoi diagram changes. So it's a nice animation to see how Voronoi diagrams may look like. Okay, this website is not about the fortunes algorithm, but it's still very relaxing and nice website to play with Voronoi diagrams. Now, the first site that I pasted on the chat box actually is a visualization of the Voronoi fortunes algorithm, the sweep line. This thick line at the top is our sweep line. Okay, so this is the line that we sweep. These red dots, they are our sites, and these are also event points originally. And as I'm going to show you, there are also other events that we are going to see. Now, the first time when we hit a site event, a parabola appears. Okay, actually, that degenerate line is not shown here because we cannot move our line infinitesimally small. So this is right now the sweep line is below this site, and it appears as a parabola like this. And as you can see, as we move the sweep line down, this is how the parabola changes. It gets larger and larger. And now another site appears, and this site actually, it's outside the boundary of our screen. It actually intersects with this other parabola. Okay, and also starts growing. Now our study structure contains only two sides, two parabolas. Now we come to the third one, and as you can see, the third one just appeared in the middle of the first one. So this is what I mean. The beachfront, which is composed of which belongs to site 1. This is the site 3, the third site we have encountered, and site 1 still has a parabola on the beachfront. So a certain parabola may be divided into two parts by these two. Now, let's see what will happen as we move downwards. Also, let me just show you the Voronoi diagram as well. Okay. Now, as I move it downwards, there is a certain, actually, not here, right? Yeah, there are certain places, actually, I think it's one of the places is this, yeah. Now, yeah, exactly. Now I'm going to show you something. The reason I'm moving it downwards right around here, a very specific event happens. It's this, look at this vertex under my mouse pointer. This is the first vertex of the Voronoi diagram that we encounter. Okay, this is a vertex of the Voronoi diagram. Now, when do we encounter that vertex? Is it on the site event? No, we still, if you look at the part of the Voronoi diagram that we know right now, this vertex is still at the unknown part. It's below the beachfront, okay? Below the beach line. Therefore, we don't still know this vertex yet. Although these three sites are processed, we have processed these three sites. This is actually a point which is equidistant to these three sites. We still don't know this vertex yet. The place where we know this vertex is right here. Right at this point, we know that vertex. What happened at that point? This parabola, exactly, the three parabolas intersect, including dotted parts. What happens is that this parabola that belonged to the first site, it disappeared. It shrank. Look at this. It was like this. As we move downwards, it shrinks, and it disappears. So, but at this point, how can we look at the sweep line? There is nothing on the sweep line. How can we put such an event? Because we are moving at discrete event points, right? So what is this? What is special about the current position of the sweep line? Because we need to put this as an event point into our event list as a dynamic event, because at that point, something changes. We need to update the study structure. We need to delete one of the parabolas from our study structure because this part of the parabola that belongs to this site no longer exists. Okay, it should be deleted from the study structure, and the new vertex should be added to our doubly connected edge list, our Voronoi diagram. But at this point, there seems to be no event. But is this position of the sweep line something special? Let's see. If you remember a vertex, what was a vertex of a Voronoi diagram? There was something related to circles, right? At this point, there's a circle that passed through these three sites, in which this is the center of the circle. But if this is the center of the circle that passed through these 3 points, so there's a circle that passed through these 3 points, okay? But what happens since this is if this is also a vertex of the parabola and it disappears at that point, it means that this is the part of also the boundary between the known and unknown, right? What does it mean? It means that the distance of this vertex is also equal to, the distance of this vertex to the sweep line is also equal to the distance of this point to the other vertices as well. So in other words, what happens is that, let me tell you what happens. When we draw the circle that passed through these three of them, the bottom point of the circle is on the sweep line. Exactly. The circle intersects the sweep line in the same actually it's the bottom point of the circle. The radius from this vertex to the sweep line is exactly equal to the radius, because that's the boundary of the known and the unknown. That's the distance of this to this side is same, the distance of this to this side is same, the distance of this to this side is same. So it's actually the radius. So it's actually when we construct this circle, the bottommost point of the circle with the minimum minimum y coordinate is an event point, which will indicate a parabola is going to disappear at that point, and it will be a vortex of our Voronoi diagram. In other words, we call this a circle event, and when these three parabolas that are adjacent to each other, we need to somehow detect whenever three sites become neighbor on the beachfront, that's a potential circle event, and we insert the minimum coordinate of that circle as an event point into our list. Okay, as you can see, the circle is not visible here. It will be good if they also added those circle events. Actually, I think there was another site with the circle events. Let me just take a look at that. Voronoi fortune, algorithm, visualization, and circle events. Maybe it's this one. No, this is the if you're interested in the code, there is also called Voronoi diagram construction using Fortune's algorithm. Let me see. I remember there was, I think it's this one. Skip to demo. Next. Yeah, I think this one shows the circle events. Let me see. No. Skip to demo. Interactive demo. Now next. Yeah, actually we have seen the circle event. Slow down. Now, can we? Yeah, actually we can slow down a lot. So let me restart it, and let me. Let's speed up a little bit, and I'm going to slow it down now. Now, the first time, when we come to the third site, you're going to see something interesting happening at that point. Because with the third site, in order to be a vertex, there should be at least three. Yeah, this is the circle. Yes, slow down, slow down. Yeah, look at this. Now, when we encountered the third site, three parabolas, a triplet of parabolas appeared on the beach line. And at this point, what we did was we constructed the unique circle that passed through those three sites. This is the unique circle that passed through 3 points. And in this case, the maximum x coordinate, if you know the circle center, if you know the radius, right? Circle center is known. We know its radius. We can actually just add the radius to the x coordinate of that circle to find the point where the circle is going to cease to intersect our sweep line. In other words, we find its rightmost point of the circle. And this point is really special. The rightmost point of the circle is a special point where we will have a vertex in which this parabola, I think, is going to disappear. So if I speed up this a little bit, well, yeah, it's going now. As you can see, right at the place where we get to the end of the circle event also disappeared, and we had a vertex. So this is what we are going to do. We are going to insert circle events to our event queue as we have new triplets of parabolas on the beachfront. We will construct a circle that passed through them. Let's speed this up a little bit. Now the third one is coming. And at this point, yeah, we are going to have our circle event. Yeah, now this is the circle event that appeared between these three, and this is the point where this parabola is going to disappear. So the rightmost point of the circle is inserted into the event queue. Okay, the actual algorithm does not go continuously like this. We don't continuously sweep the plane with this line. This is just for visualization purposes. We actually jump from event to event discretely. Okay, now one thing that may happen is that some of these circle events that we identified, they may be false alarms, like this. For example, what if right at this point another site appears here before we come to the end of the circle event? If a site appears right here and actually it causes this vertex to disappear, so which means that that vertex is never going to be realized as a real vertex of our Voronoi diagram. So sometimes there may be sites that may appear before the end of the circle that may cause removal of that parabola due to another reason, not due to a vertex. So we may have false alarms, and we also need to detect them. So what we will do is in our plane sweep algorithm, whenever a parabola disappears due to something else, if there was a circle event associated with that parabola, we need to remove all of the circle events associated with that disappearance of that parabola. And as you can see, the beach fronts, they trace out the edges of our Voronoi diagram. So yeah, this link is also good. You can also try this out by interactively. Let me also paste that link here. All right, so we have now an idea about how we are going to proceed in our algorithm. Okay, we will have two types of events: site event, circle, and look at this. This circle is really large. So there's actually an event right now. We don't see that event actually. Look at this. At this point, a new parabola appeared, and this parabola is in the middle of these, a new triplet. It's due to this side. No, not this side. That parabola was, I think, it's this one. This shouldn't be there, right? So this circle event is actually, I don't know, maybe we encountered it earlier, but it's the circle that passed through these 3 points. Oh, probably it has still a parabola over there, maybe. That's outside our view, but this is the circle. Sometimes the circles may be very large, which means that there will be a vertex event way over there. Yeah, this one is much smaller, as you can see. A site appeared here, and this is the circle event. But the purpose of circle events is to update the beach line, because at that point parabolas disappear, and we also update our Voronoi diagram at circle events because the vertex appear. All right, now I'm going to just stop this one. There's no stop button, so it will keep running, or I can just close it down. All right, so the circle events are not shown here, but the parabolas appear, and here at this point, for example, there is a circle event at this point where this parabola in between disappears. And the circle event, I think it's the bottom point of the circle that passed through these 3 points. Yeah, it's exactly like that because it's the vertex of these 3 sites. And it goes on like this until we process all the site events and circle events, which, if for example, after we process the last site, there may still be circle events, like for this vertex. But after the last circle event is processed, it means that we have found all of the vertices of our Voronoi diagram. Some of the edges may still continue all the way to infinity. We're not going to continue our plane sweep to infinity. After we finish all of the vertices, we can draw a bounding box around the Voronoi diagram and connect these unbounded. If there are still parabolas in our sweep line, it means that these are those unbounded edges, and we connect them to our bounding box. So this is what we can do to practically visualize a Voronoi diagram. Now, let's go ahead and take a look at the pseudocode is not given on the slides. This one just describes again what a circle event is. As you can see in a circle event, we determine a vertex of the Voronoi diagram. Site events, circle events. In a site event, a parabola appears in the middle of a parabola. So there's also some other observation in the book. A parabola is going to appear in the beachfront only due to a site event. So that's something interesting. As we move downwards or as we move right, a previous parabola cannot break through existing parabolas. So parabolas are only going to be introduced into the beach line due to site events. Okay, and that's where a new parabola is going to appear. When we are moving the sweep line, some previous parabola cannot come in front and break the beach line. Yeah, so this one, yeah. The parabola cannot appear on the front by breaking through from behind. A parabola like alpha here, this will never appear. Alpha will not become thinner and break through the existing parabola. And at circle events, here this W is a circle event in which the unique circle that passed through these points P, Q, and S, that's the rightmost point of that circle. And in the center is that point U that becomes our vertex. And another thing is that this alpha and gamma, these two parabolas, we will not have something like 3 consecutive parabolas. In a circle event, we will not have alpha, beta, gamma. Alpha and gamma belong to the same parabola. They should belong to different sites. That's how we define the circles. And I talked about the study structure, how actually it's a balanced binary search tree that contains the sites, the leaf nodes, and the intermediate nodes are pairs of sites that indicate breakpoints. So we have talked about this. Now I can actually talk about the algorithm directly. And for this, I'm going to now jump to the book, all right, and go over the pseudocode to make everything clear. All right, these are the things that we discussed, and also the edges of the Voronoi diagram are traced out by breakpoint lines. And sometimes there may be multiple sites. I think this is the case. Or no, this is showing the circle event. Now, let's go over the pseudocode right here. Okay. The main algorithm is exactly the same as any plane sweep algorithm. So we have a study structure. We also initialize our output. The doubly connected edge list is also constructed on the fly as we process the events. While the event queue is not empty, we get the next event and we process it. And since there are 2 types of events in our case, we handle site events separately and circle events separately. The site event gets the site information as a parameter, the point that is given to us as input. And circle events are associated with the parabola that is going to disappear. So here gamma is the leaf of the leaf node of that study structure. It's actually denotes the site, okay, and it represents the arc, the parabola that is going to disappear. So we just associate this gamma with a site here. And after step 6 is completed, we finish our algorithm. Step 7 and 8 are post-processing cleanup steps to get the bounding box around our Voronoi diagram and to get rid of these infinite edges, connecting them to our boundaries. So that's step 7 and 8. Now here is the important part, which is described. I mean, look at the pseudocode. It's just like a paragraph written step by step. And this is also like that. So it's like a huge paragraph in 3 steps. So how do we handle site event? If the status structure is empty, we just add the site into it as a single leaf node, and that's it. If the status structure is not empty, we do the search for the arc that is vertically above the site. So this is the example I showed here. Okay, if this is the site, we search for 2. How did we search for 2? We use these pairs and breakpoints. We went left or right until we end up at a leaf node. There may be some degenerate cases that we didn't discuss. For example, what happens if a site is directly below a breakpoint? In that case, for example, we will see that, we will either, when we try to ask the question, for as a breakpoint, for example, between 5 and 6, is it on the right, left subtree or right subtree? It will appear exactly on the breakpoint. So we can resolve those degenerate cases. For example, just putting the equality part to the left side. We can also do that. Just like we break equalities in regular binary search trees. If it is exactly on the breakpoint, we can put it on the left subtree. We can put it on this parabola 5, for example. All right, so we search for the arc that is parabola that is above pi. If the leaf representing that alpha has a pointer to a circle event, so if that arc was going to disappear due to a circle event, then that circle event is clearly a false alarm because there is a site that appeared there. That parabola is no longer a single parabola. It's divided into 2, and therefore that circle event we had written earlier, we have put into our queue earlier, was a potential circle event, but it's not going to be realized as a real circle event. So it's a false alarm, and we delete it from our event queue. So that's why we need a dynamic event queue where events can be deleted. So we also replaced the leaf node with 3 new arcs. The arc that is to the left, so it becomes something like this. If you look at this picture here, now it will be, this is alpha, this is the new site. Do we have a name for it? Do we say gamma or just no? The arc that is represented by this pi. So pi's arc here and the alpha that is to the right hand side. Okay, so it's going to be the single leaf node that was 2 is going to be replaced by 2, pi, and again 2. So it's going to be replaced by, there will be an intermediate node, the tuples pj pi and pi pj, representing the new breakpoints. There are 2 new breakpoints that are happening, and these 2 new breakpoints become 2 new intermediate nodes with 3 leaf nodes underneath them. And at this point, if the tree becomes unbalanced, we make it balanced again. So if you're using AVL trees or red-black trees, call their necessary functions to restore the balancedness of the tree. This is what it's saying. And after this point, we also, since we had now inserted a new site, a new parabola appeared, 2 new edges. Half edge record starts as 2 breakpoints between these 2 things, separating these 2 sites. They will be traced out by these 2 new breakpoints. So we create new half edge records. Their start points are known, but their end points we don't know that. And we check actually we don't even know their start points. We start tracing out the edge as if it's in the middle, because there may be a vertex that is above this event point. We start tracing them. So let me show you on an example here. Look at the point where actually maybe this one is going to be better. Yeah, look at this. Look at the point where the sweep line hits this event point, where we are going to get a new parabola. And look what happens. Look at this edge, the green edge. The parabola, I mean, these 2 breakpoints, they trace out the same edge as you can see. Okay, towards left and towards right, this is a single edge. So we started tracing the edge of this right in the middle. So it's not, we don't know the beginning or end point of this edge yet. We're going to figure that out when we come to a vertex event, a circle event. So, but a half edge record should be started at this point, which will be finalized when we come to circle events. All right. So we create half edge records. We also, due to the introduction of this new site, there will be new triplets of consecutive arcs in our beachfront. And for each triplet, we construct a unique circle that pass through these three sites, and we insert them as potential circle events to our event queue. So we also see, we only do this if we see that the breakpoints converge. If so, we insert the circle event into queue and add pointers between the node, the corresponding node in the study structure, the site, and the node in the event queue, the circle event in the event queue. And we do the same thing for the triplet that appears, the new triplet that appears on the left and the triplet that appears on the right. These are new triplets, the new triple sites that may be potential circle events. We add them to our event queue. So this is how we handle a site event. Lots of bookkeeping and lots of things to do. New circle events, at most 2 circle events may be added due to this. New edges started. We start tracing new edges. We create, we update our study structure, and we also may remove existing circle events in the event queue. So these are the things we do on a site event. And on a circle event, the first thing is we need to update the study structure to delete the leaf node that is going to be removed. And we also update the tuples representing the breakpoints at the internal nodes, because something disappears, the breakpoints disappear, so intermediate nodes should be updated. Again, we perform rebalancing operations as necessary, and if there were any circle events involving this breakpoint that is now disappeared, involving this arc that now disappeared, we also delete them from the event queue. Now, the center of that circle, at that circle event, what happens is we identify a vertex of the Voronoi diagram. We add that as a vertex record to our doubly connected edge list. And these 2 half edge records we already had, we actually finalize their starting points. Their endpoints may still not be known. We check also, due to the disappearance of the arc, now the triplets are going to form, a single new triplet is going to form on the beachfront. We also check whether they form a circle event. There is a circle event below the sweep line, and we add that circle event if necessary. There may be 2 new triplets actually. The former right neighbor now is the middle arc. So it's like this. Let me just draw it here. So imagine this one is the one that disappears, the small one that disappears, and there are 2 other ones to the right. So this is going to disappear. After this disappears, a new triplet, this one is a triplet, this one is a triplet, right? I mean, after this disappears, we get ourselves new triplets. Triplet 1, triplet 2. These are the potential new circle events that we may have. And when do we have them as circle events? If these breakpoints, if we have the equations of these breakpoints as lines. If they converge, means that there may be cases where they move in different places. Look at this. I just showed you 2 cases where the breakpoints converge at some potential point. So this may be our circle event. And sometimes the breakpoints may diverge, meaning that the circle event actually happened above the sweep line. They are diverging from them. So in this case, there will for these 2 breakpoints, there won't be a circle event that's happening below the sweep line. Therefore, we don't add a circle event if the breakpoints look like this. If the breakpoints converge, like this, if they're going to intersect below the sweep line, then we add a circle event. So this is what the book is saying about the convergence. If the two breakpoints of the triplet converge, we add that as a circle event. And that's it. That's the whole algorithm. This is how we handle these two types of events, and we create our doubly connected edge list. Again, this website is a very nice visualization of what is going on as we have these things. At a new site event, an arc appears, and the study structure is nothing but a sequence of sites that contribute to parabolas on the beachfront. And if you understand the structure of the study structure, how it is, what the internal nodes represent, and it will not be very difficult to implement these updates. All right. And I think I'm not going to talk about sections 7.3 and 7.4. I'm skipping those. So Voronoi diagrams for line segments, and Voronoi diagrams 7.4 is farthest point Voronoi diagrams instead of looking at the closest distance. So this is something that is interesting. I'm not going to talk about these two sections. So we're just going to talk about the fortunes Voronoi diagram algorithm, and that's it. As you can see, this was another plane sweep algorithm that we have seen. It was a more advanced plane sweep algorithm than the previous ones. We had dynamic events that appear, disappear. We may sometimes, I think this is the first plane sweep algorithm we have seen where an event has to be deleted from the event queue. Okay, so we may have some false alarm events that we may need to take care of. And I think that's all I want to talk about the Voronoi diagram algorithm. The complexity is O log n, because at every event point, we just perform operations on the study structure that takes log n time. All these updates, the other updates, they take all one time. And since the number of vertices are linear, it means that the number of circle events will be linear. And the number of sites are also the number of events that we process at the end is linear, and if we just spend all log n time for each of these events, at the end we are going to have an O log n algorithm to compute the Voronoi diagram. All right, so that's it from me today. Do you have any questions, any parts that you want me to go over again, or you have some questions that you didn't understand? I will be happy to answer them. Okay, it seems like you don't have any questions. I also suggest you read the book if there are parts that you don't understand. The book also describes the algorithm in detail very well. So then that's it from me today. See you next week, and we are going to talk about chapter 8, which is arrangements and duality. We are going to solve a problem related to ray tracing, but we haven't seen this part of ray tracing in our computer graphics class. So let me just quickly go over as a motivation, as a teaser. Let me show the problem that we are going to talk about. And the complexity that we are going to achieve is going to seem impossible at first, but it will be possible. So it's a really nice problem. Given a square, our problem will be to generate some random points within the square. So in the context of ray tracing, the square actually will be a pixel. In regular ray tracing, we shoot our rays to the center of this pixel, right? So if you want to increase the resolution of your image, if you have a raw resolution image, shooting at the center of this pixel will cause some artifacts at the boundaries of, at the edges of objects. You will have some zigzags due to this discrete nature of the pixels. One way to resolve this is to increase your resolution of the image. Another solution that this book provides talks about is called supersampling. This supersampling is the process of, instead of shooting a single ray for each pixel towards in their center, why don't we shoot, for example, multiple rays, for example, 10 rays per pixel? This will decrease the running time complexity tenfold, but it will decrease these artifacts. Now, the question becomes, if you're going to shoot random rays that pass through this pixel, how random these, for example, you're just going to select some random points from here. If they're 10 points, so this seems like a good random distribution. But how can we measure the goodness of a certain random sample? For example, if somebody else gives you 10 points, which are all here, obviously this is a very bad distribution of random points in this square, right? Because if you're going to use them as super sample, it may even be worse than shooting single ray from the center. We will have a huge part of the pixel not even considered at all. So the problem is, can you a set of random points will be good if the maximum, if you can draw a line that passes through this circle that will separate it into two in such a way that all the points are on one side and there are no other points on the other side. If this area is very large, the area where there are no points is the ratio of that to this area of the whole circle is very big, it means that it's not a very good random sampling. So our goal will be given to actually measure the goodness of these random points. We will be given a set of points, and our goal will be to find this line. Find the line that is going to maximize the empty region. Okay, which line that you draw maximizes the empty region in this square. So it's like an optimization problem. So we are going to try to maximize this line, and the smaller this area is, maximize this area, the smaller this area is, the better these random points are. So we will actually solve this problem in linear time. This is going to be amazing. Okay, it seems like an impossible problem at first. So one thing that you can do is, for example, for every pair of points, you can draw a line and check whether all the remaining points are to the left or to the right. Actually, it gives you an n-cube algorithm. The brute force is an n-cube algorithm. I think we're going to reduce this to n squared, not O n. I'm not sure. I'm going to take a look at that for next week. But the brute force algorithm is like this. It's obvious that any line that tries to maximize this or that, for example, if I draw a line like this, you can move the line towards the points. So they will pass through 2 points. Okay, so draw every possible line that passed through 2 points. There are O(n) squared such lines. And for each of these lines, some of them are not valid. Some of the points are to this side, to this side. For all of these n squared lines, check whether all of the points are to one side. That means O(n) processing for each of those lines that results in this O(n) cube algorithm. And we are going to reduce this greatly. Okay, so this is what we are going to be doing for next week. All right, that's it from me for today. See you all next week. Bye-bye.